My name is Martin Fuller. Welcome to my talk on advanced mesh shaders and how I learned to stop worrying about beating the hardware and find some new opportunities. So briefly, I'm going to cover the input assembler, trying to beat the input assembler, trying to beat the primitive assembler immediately before rasterization. I'm then going to talk about Per-Meshlet bounds, a new culling granularity, advanced culling, and I'm going to finish off with index compression. So, strategies for beating the input assembler. So we have two pieces of hardware that support mesh shaders currently. We have NVIDIA Turing cards on PC, and we have the Xbox Series X. NVIDIA Turing, certainly at this point in time, group size of 32 seems to be the sweet point by quite a long way. So this is happens to be the size of a single wave, and this in fact is exploitable. It's much cheaper to do things like compaction if you only have one wave involved. You're not working across group. Of course, this is PC. There will be, driver updates, new pieces of hardware. I recommend that you test that this group size is a win for you. The Xbox Series X actually supports group sizes up to 256, so this is larger than the specification maximum of 128. In my testing, 256 was in fact the best group size to go for, hands down. And the reason for this was the larger your group size, the better the vertex sharing. And in fact, if you had an infinite group size, you would only ever transform each vertex once. Clearly not practical for on-chip memory, but this is the reason why larger group sizes are working out better on the Series X. So where do we start? So we start with an index buffer. We're probably starting with a vertex cache optimized index buffer, which every title has already. And it turns out this is a pretty good starting point. We just keep going up until we've filled up the group either with triangles or with vertices, whichever caps out first, and call that a meshlet. And it turns out we can do better than that. So if we add in candidate triangles to a meshlet, and we add the triangle that adds the least number of new vertices, that's a pretty good heuristic. And then as tiebreakers, if we have more than one triangle that wants to add, say, one new vertex, then we can add the triangle that adds the least new volume, for example, for biosphere culling, or the least increase in cone angle, or a triangle that is otherwise an orphan. And this is where possibly a greedy algorithm is not great. We want to kind of hoover up orphans because these guys are going to have to be collected at some point. And if you have a single triangle left on their own, that's going to be one triangle and three vertices, which is a pretty awful ratio for us. So we want to be sympathetic and not too greedy in our algorithm. So this is what the meshlets look like, a very simple color per meshlet. So on the left, we just took the index buffer and chopped it up, very quick. And on the right there, we added the triangle, added the least number of new vertices with sphere volume as a tiebreaker. So we've got roughly spherical meshlets for the most part, very good, but a few kind of remainder meshlets which are funny shapes or a bit larger than perhaps we'd like. So could I beat the input assembler? Straightforward mesh shader. And the answer is yes and no. And it depends very much on mesh quality. And what I mean by mesh quality, for the most part, the most important factor is thread utilization. So how many dead threads am I carrying around to render this thing? How many times have I got threads turned off in a vertex phase or a triangle phase? And if you think about it, the worst case mesh generates just one meshlet. And this one meshlet wants to use 51% of our threads, and the other 49% are dead. And obviously, when you come to instancing, you can't pack more than one instance together into the same group. So this guy is a kind of meshlet disaster. The secondary consideration is what is the ratio you're getting in vertices and triangles. Your kind of minimum workload that you can't escape is a thread per triangle. but how many times are you having to retransform vertices? How many times have you got groups that are not fully utilized in their triangle phase? So we ideally we'd be at less than one vertex a triangle. Quick survey of AAA games, we're somewhere around that ballpark, 0.8 to 1.6. The demo meshes that accompany this talk are better than average. And the other consideration, of course, is what is the impact on overall frame time if you're using async compute and you're tying up compute resources with mesh shaders. You know, you've got to measure all this stuff. Your mileage is going to vary. But yeah, it is certainly possible to be the input assembler on both NVIDIA and the Xbox Series X. So just going to skip out to first demo. Hi, so demo time, slightly improvised circumstances. So I have my Meshlet demo running on a couple of different devices here. So first up, Windows 10, NVIDIA 2080 Ti, and on my right, Xbox Series X dev kit, running on a nice big OLED. So the first demo I'm going to show you, I should first explain the scenario. So this is a very simple kind of mock-up, 5 rooms, and this, I can toggle the transparency of the walls, and this at the moment is demonstrating how culling typically works right now with a per-mesh bound sphere. So when the bound sphere is determined not to be visible, we stop drawing the mesh, like this. And that's just a sort of on-off binary decision. And then when the actual doorways stop aligning, we stop drawing the room as well. So then we have the doorways aligning and non-aligning. And this is more or less the way, you know, the majority of titles work right now. They might use a box rather than a bound sphere, but pretty much that's how titles work. So now I've kind of explained the little demo world. I'm going to go and have a look at one of these meshes. So here we've got our robot, mesh shed time 34 microseconds, so 34 millionths of a second, with a vertex shader 33.8 maybe, 34.7, so just fractionally slower with a mesh shader than a vertex shader, although this is using the index compression that I will talk about at the end of the talk. But it's all down to mesh quality. So how well did it, how good is the quality of the meshlets? So here again, rendering with the mesh shader, 37 microseconds, and the vertex shader just 38. Just ticking into 38. This is such a small amount of time. This is only just we measure to this kind of precision. So the next question is, can I beat the primitive assembler? So this is kind of fun. Takes me back a bit. Obviously, you have you know, the number of triangles here is not the number of vertices in your meshlet is not 3 times the number of triangles. You've got some vertex sharing, and this is exploitable. So what I'm doing here is I'm testing a vertex against 5 different clip planes in a unit cube clip space, and then the Frustum culling becomes incredibly simple. We're just doing 3 loads from group shared memory, which is very, very fast, and bitwise AND tells us whether the triangle is visible or not. So this is quite efficient. However, I found this is not the way to go necessarily. We're always testing against 5 planes here, and we've had to produce the clip space position, which is something that possibly, if there were no triangles visible at the end of this phase, we could have avoided computing. So we want to defer the production of the clip space position if we can. Instead, I came up with this. This is better for a couple of reasons. Firstly, that yes, we're using the world space position. Secondly, the number of planes is highly variable and arbitrary. And you will find quite often that a mesh might clip kind of the left-hand clip plane, but not the right-hand clip plane, or the top and not the bottom. So the number of planes that you actually have to test against per meshlet may be as few as 1 or 2. It's frequently no more than 2. So this turned out to be quite a good win. Next, the next issue is how to tell the GPU that we've culled a triangle. There's multiple different ways of doing this. So SV cull primitive is a per triangle piece of metadata we can export from a mesh shader, this SV cull primitive. The hardware is able to optimize this. This is probably the recommended route. We could write out degenerate triangle. We've found on Xbox Series X, this is actually slightly slower than SV cull primitive. Or we could do manual compaction. We could say, you know, there's 90 triangles, whatever, survived culling, so we're going to export 90 triangles and we're going to put them all in a linear array. So we've got to do that compaction work. The nice thing about this is that we actually know the total number of visible triangles that we need to export, and if that number is 0, then we can skip attribute shading. So this might be other things that you compute per vertex, like global illumination. So just diving into attribute shading very briefly. So mesh shaders can work, you know, it's entirely up to you. It's just basically a attribute shader. You can do whatever you want as an input and processing, as long as you export your triangle list and your vertices at the end. So a mesh shader could work in 3 phases. So the first phase would be compute position. That's a thread per vertex. Your second phase could be a thread per triangle doing the culling. And then the final phase is back to thread per vertex, and this is doing your vertex attribute shading. And you're only going to do that if you have triangles, like any triangles that survive culling. So you're exporting at least 1 triangle, and potentially only the vertices that survive culling. So for that, we need compaction if we wanted the minimum attribute shading cost. And the algorithm for this is fairly nasty, in fact, but relatively simple to implement. So we have a group shared array to say 1 D word per vertex to say whether it's referenced or not after culling. We have to pre-zero that array ourselves. And for every visible triangle, we write a 1 into the array for each vertex. Then we have to do a cross-group compaction of all the reference vertices, and then we have to re-index the visible triangle array from the original index to the newly compacted index. That's fairly expensive, and we're only going to get a saving if at least 1 wave gets to skip out earlier and not do any attribute shading work. This is one of the places where wave 32 can be a win over wave 64, but I couldn't make this pay for itself. So a much cheaper version is a simple binary, are we going to do attribute shading or not? And this depends on us having at least 1 visible triangle. And here again, kind of having a group size that's the same size as your wave is incredibly advantageous, because you just have to do a cross-line intrinsic. So this wave active count bits, and that will tell you straight away whether you can skip attribute shading. If your group is more than 1 wave, it gets a bit more complicated. You have to sum up the results from each wave. So did I beat the hardware? So the input assembler, yep, that's entirely beatable, but it's all down to meshlet quality and your tooling around that. But were you input assembler bound, or were you running some async compute at the same time? I managed to match the hardware speeds for camera frustum and backface culling. Couldn't manage it for zero area, but if zero area is a thing for you, you probably need to have a conversation with one of your artists. So yeah, not that impressive really. Trying to beat the fixed function hardware blocks is tough. It's probably better to let the hardware do backface, zero area, camera frustum, and you can concentrate on doing more interesting things, unless you have a very, very high attribute shading cost, in which case this may still be attractive to you. So, how did I learn to stop worrying? And the fact is that mesh shaders open up, and amplification shaders open up some really interesting new things that we can do. We're not just trying to beat the hardware at our own game, we're advancing and doing things that the hardware really hasn't enabled us to do. So the first of those is Per-Meshlet culling. So we have a bounding volume Per-Meshlet. This hasn't been a practical culling granularity. And then we have that combined with kind of advanced culling techniques. So whether this is constraining the frustum with portals, anti-frustrums with geometric occluders, depth image occluding from a depth image, or normal cone culling, and then finally mesh. So very, very quick recap. I'm sure most people will be familiar with these techniques. We have an eye, a camera in a room with a frustum, and we can see visible objects in green, a clipped object in yellow, which we would have to draw ordinarily in entirety, and then a red object got culled. And then we produce sub-frustra. So for the next room, so we've got an object we're going to have to draw, an object that got culled, and another sub-frustra for this second room with an object that's clipped. And then in the anti-frustrum case, we have very, very simple occlusion geometry, creating a frustrum whereby if an object's entirely behind all the planes, then it's considered not visible. And again, you can get the clip state for certain objects. The interesting case here is the clipped object. So drawing a mesh, yes, no, binary decision, been around forever. But now we can do something extra about this clip state. So when a bounding sphere has been classified, or a bounding box has been classified as clipped, then in the mesh shader, we're going to test the Per-Meshlet sphere against the planes. We're going to do a thread per plane, and then every wave in the group is going to do its own sphere test. So they're all going to compute the exact same visibility result, but this saves cross-group communication at a sync point. It's not that efficient. Most threads in your group are dead or duplicating work, but it's only a sphere test and you're doing a thread per plane, so it doesn't take all that long. More efficient, however, is an amplification shader. So we can be testing a meshlet per thread, and we loop for the number of planes. So if you have a medium or large number of meshlets, multiply that up, of course, by your instance count. That's far better utilization of the GPU. Conversely, if you have your kind of worst case, one meshlet, one instance, your amplification shader is going to spin up only one thread in the entire group, which is not efficient. But that doesn't tend to happen very often. In a real title, we expect the amplification shader to be a win, hands down. So some tips. So first off, per instance bounds testing, that is essential. So this is what you're doing already for determining whether something's visible, not visible, or clipped. So we're only going to go down this clip path for objects that need it. Secondly, minimize the number of planes is key. So for the Per-Meshlet testing, I found there was no point in sending a near or far plane. The meshlets are sufficiently small that just the 4 main planes would do. And then I would only planes that intersected that sphere are transmitted, and only if they intersect by a non-trivial amount. So if they're only just glancing the sphere by, say, 5%, then I don't bother sending that plane. And then, of course, finally, the best fitting bounds you can come up with the smallest volume, the better. No surprise to anyone. Here we have culling an example, and we only need one plane to achieve this. Cutting down the number of planes is very important. Something the amplification shader can do for us, which is quite attractive, is we can further refine the planes. So we've been told by the CPU that we need 3 planes, for example, 2 or 3 planes, quite commonly 2. And then we can test Per-Meshlet how many of those actually clipped that meshlet sphere, and we can send a bits mask of which planes within that little array that the CPU generated should actually be tested by that mesh shader when it's doing its per triangle culling. And the answer, in fact, might be 0. It might be that this particular meshlet isn't clipped by any of the planes at all, so we can skip back out of doing per sphere testing, per triangle testing for that particular meshlet sphere. Code example there, very, very simple. And this is, of course, the same mask for every thread and the mesh shader. So this is wave invariant or thread invariant. So which type of shader should we favor for doing the sphere test? Should it be the amplification shader or should it be the mesh shader? And with big meshes, with lots of spheres and lots of meshlets, largely culled, then the amplification shader won hands down. We didn't even spin up a mesh shader for a number of meshlets, and that's a big win. If we had no culling, so the mesh shader, the amplification shader was run, and it classified everything as visible. Perhaps it managed to find the plane count, but we ran the same number of mesh shaders as we would have done before. They didn't have to run the sphere check, but it turned out to be a bit of a wash. So in these two scenarios, we've got either a wash or a big win for the amplification shader. So amplification shader looks like a good idea. Again, if you have a very small mesh with a low number of meshlets and a low instance count, the mesh shader can beat the amplification shader by a small amount. The amplification shader just couldn't go wide. That's probably not at all common in a real title. So we think you should prefer amplification shaders. The main thing here is to make sure that every thread in an amplification shader can potentially be processing a different instance. That's super important. So what about doing per triangle culling against a reduced frustum? And again, as happens time and again with mesh shaders, the win you get depends, and that word depends keeps coming up. And it depends on the amount of pixels that you've saved, and it depends on the cost of the pixel shader and whether those pixels would have failed the depth test. So in my particular demo, you will notice that the pixel shader is extremely simple. I don't read multiple textures. I don't in fact read any textures. I'm only writing out to one render target, so not 4 or 5 G buffers or whatever. So the pixel shader is very, very cheap. You should expect bigger wins from this. Again, you should only be doing per triangle testing against meshlets that have been clipped, tinted red in the demo. It's possible that you could have a flag on your meshlet or a weight that says this meshlet only consists of very, very tiny triangles, so don't ever bother doing per triangle testing on this one. Or conversely, this meshlet's got some huge triangles, so you definitely should. So here we go, demo time again. At the moment, we've got this kind of just a single bound sphere test per mesh, as we had before. And now we're going to switch into testing each meshlet's bound spheres. So as the bound sphere becomes visible, so we start drawing its triangles and vice versa. The helmet's quite low poly. If I take the dragon, for example, this is quite high poly. And we can see this is a new culling granularity that's never really been practical in the past. If we go to fully opaque walls, you can see that you're always getting the correct image, obviously vitally important. But under the hood, we are drawing less and less of this guy. So what does the performance look like? So there we have drawn in the full thing with the mesh shader. So 102 microseconds. I should emphasize that this is running at 4K, whereas PC was running at slightly under 1440. Obviously a lot more triangles in the Dragon mesh. When we go to meshlet, to culling these meshlets here, we've almost halved the time, so 53 microseconds. And then of course we could be doing the testing per triangle. So I have another mode here, and in this case if a meshlet's been tinted red, that's because that is a meshlet that's been classified for doing per triangle testing. If it's not been tinted, it isn't doing per triangle testing. And we can see here that we're incredibly close to this edge. You know, the number of wasted pixels here is extremely low, and that's purely down to the tessellation of the dragging. And we end up doing quite a lot of testing per vertex and per triangle for relatively small number of pixels saved. You can see the wastage there. But if you take something, for example, like the robot, where the triangles are a bit bigger, so here we have a 39 microseconds robot. We start culling individual meshlets, 34 microseconds, that's quite a healthy saving. But then if we toggle to doing per triangle testing, you can see we're saving quite a lot of pixels here. So 34 microseconds goes down to 26. So again, you know, we haven't quite halved the rendering time, but we've made a significant reduction. And of course the real titles pixel shaders will be a lot more complex, certainly involving multiple textures, which of course this demo is not. So we saw some good results. The biggest leap is going to per-sphere culling. So going from a vertex shader or a pass-through mesh shader down, you know, culling the spheres, that's a huge win. In my case, you know, dropping down to doing per triangle testing, there's a fair amount of math involved in doing per triangle testing, even with a reduced number of planes. So I was getting a small win from that. But of course, as I say, your mileage is likely you'll get a much better win because your pixel shaders will be more complicated than mine. And then, of course, the same holds true on the NVIDIA 2080 Ti that I tested at 1440p. Huge win just from going to sphere culling. Smaller win, particularly with the Dragon Mesh, which is so highly tessellated from Triangle Culling, but you can see it is still a win. And the amplification shader here was generating some benefit as well. So yeah, very worthwhile. So what we in fact end up with is potentially 3 different PSOs for drawing your mesh. So the first case is that your mesh is entirely visible, and we're going to just draw it with a pass-through mesh shader. It's not going to do any culling at all. Then we're going to, well, we might have more than 3 PSOs, sorry. So then we're going to say, do we have a large number of instances and a large number of meshlets, in which case we should be doing a sphere check in an amplification shader. Otherwise, potentially we might want to do it in a mesh shader, but I would check your mileage on that one. Then, of course, is it clipped by the camera frustum? Because if it is clipped by the camera frustum, then there's no way we're going to save any pixels because the GPU would never render outside the viewport. So we probably just want to do the sphere check. We want to run a PSO that does the sphere check in an amplification shader, and then the mesh shaders again basically pass through. Only if the frustum is in some way reduced, so we have some potential for saving pixels, pixel shader work, and we have, say, large triangles or expensive triangles, then we want to go down the full route where we're doing the sphere check, probably an amplification shader, and the mesh shader is also doing per triangle work, but again only for clipped meshlets. Fairly straightforward. Yeah, it's absolutely worth stressing that your mileage may vary and will vary. You should test all of this for yourself. Lastly, I'm going to talk about index compression. Fairly straightforward. So we've had the concept of a base offset for indices for a long time. So now this base offset becomes Per-Meshlet. So now after having this base offset, we found our minimum vertex index, we find our maximum, and then we work out how many bits we need to store the delta. So in this particular example case, we have a base offset of 900. We have a maximum vertex index of 1100, so we need 8 bits. So you can see straight away we're getting some nice compression there. And then of course we have the triangle indices. So if you have 128 triangles, you need 7 bits per triangle index. So that's going to compress down to 21 bits each, which is a lot less than a 32-bit D word. So it's easy to see where the opportunity for compression comes. So in terms of storage, I implemented this as a single byte addressable buffer for both sets of indices. The indices start on the D word boundary. I load n D words into group shared memory. And then once that's done, then each thread has to unpack from essentially what is a bit stream, the bits it needs, the indexes. And this will, sometimes it can get the entire index from one D word. Sometimes it's been split across 2 D words, so it needs to read the high D word and the low D word and combine them. It's very trivial, very straightforward stuff. Nice optimization for triangle indices was to pack them all together. So say that 21 bits of 7 indices will read at most 2 D words to get the 21 bits. And then they will be further split down into the 3 7-bit values. Decompression essentially looks like this, and it's fast enough to do on the GPU every frame. But if you were running on a PC that didn't support meshlets and you had packaged only meshlets, it's incredibly fast for the CPU to turn this back into a regular index buffer. The unique vertex index and triangle arrays here are bit streams. They're compressed. Very, very easy to extract the values. There's a bonus slide on that. So what did it give us? So it gives us savings in storage, it gives us savings in load time, it gives us savings in RAM, and it gives us savings in bandwidth. If we take that 202,000 triangle dragon, that had to use 32-bit indices, and we made a huge saving here. Actually saved 1.5 meg out of the original 2.3, so 60% off index buffer saving. The robot mesh actually is very, very rounded. It has more triangles than it looks because of the rounded corners. So we were almost at the limit of 16-bit indices with 63,000 triangles. So the index buffer here, we saved around about 29%. And then if we look at sort of the low log dragon, was comfortably within the 16-bit index range. Again, 29%. Seems to be around 29-30% for 16-bit indices. So quite a nice saving. In terms of GPU performance, you're obviously spending vector arithmetic, integer arithmetic to unpack these things. There's some shifts and ands and that kind of thing in there. So it's fairly trivial stuff, but there's a cost. Even with index compression, I could still beat the input assembler for good meshes, for the best meshes. For some other meshes that didn't build out quite so well, ended up about 5% slower than the input assembler. And the conclusion really is that there's no free lunch. You get what you pay for. If you want to spend some of the GPU resource doing decompression, then that's up to you. The mesh shaders give you the flexibility to do that, whereas it was previously not practical with just regular vertex shaders. I feel that, yeah, the amount of RAM we're spending on geometry has gone up considerably with ray tracing, having two versions of the geometry in RAM. So it's good to use mesh shaders to fight back and get the RAM down again. So takeaways. So Per-Meshlet bounds and advanced culling, this is the really good stuff. This is where you can take your mesh rendering time and halve it. So you're getting this kind of clipped state is now very interesting to us. We can get some big perf wins there. Doing the culling per triangle, I would say, is only useful if you're saving pixel shader work. So again, not the edges of the screen, anywhere where you can reduce the frustum. Yeah, and again, I will stress that in my demo, the pixel shader was dirt cheap. So your mileage should be considerably better from doing per triangle culling than mine was. And the amplification shader, despite the name, it can also be very useful for culling, reducing workloads. Trying to beat the hardware at its own game is tough. That's right now, trying to beat the input assembler, trying to beat the primitive assembler. In future, that may be more viable. We don't really want to be spending die area on these things in future. We'd rather go to a software solution. And then mesh compression was super interesting to go and experiment with, saving 30% on image size, load times, memory bandwidth for 16-bit indices. Pretty good return, up to 60% versus 32-bit indices, and removing the need to split big meshes into multiple draw calls is attractive. So yeah, that was a really interesting experience. Of course, there's lots of things to try in future. I think we can do a lot better with the meshlet building, particularly log generation. I think should be meshlet quality aware. This is how we're really going to beat the hardware, by having these super efficient meshlets. Normal cone culling, I've done some experimentation with that. It's ongoing, but it looks like the best place to do that will be the amplification shader, possibly multiple cones, a cone per wave, because particularly on the Series X, the large size tends to produce quite bad clusters unless you can break it down. Occlusion culling and amplification shader, that's going to be super interesting. So obviously we want to load up the depth image just once and hit it with as many spheres as possible. We don't want to be loading it up for one sphere in the mesh shader. Vertex buffer compression is also possible. Ray traceable meshlets on Xbox Series X, also possible for saving memory. And of course, tessellation. So that's it. Thank you very much for your time, and maybe we'll see you in person at a future GDC.